All right, so we have one final section we're going to look at in our first unit, which actually in your book jumps up to something in chapter 3, but it's still part of our same story of limits. We're going to take a look at section 3.5 about these things called limits at infinity. And what today is going to do is this is going to give us some language for talking about what happens on our graph far to the left and far to the right. This is all about what happens on our graph far to the left and far to the right. Let's take a look at this function, f of x, that I just drew. What we're going to look for is the limit as x approaches infinity of f of x, and we're also going to look at the limit as x approaches negative infinity of f of x. The limit as x approaches infinity, well, this is really saying as x gets really big, as we go way far out to the right. Is there a y value I'm getting close to? Yes, there is. My graph is getting really close to the y value of 3. The limit as x approaches infinity is 3. In a similar idea, the limit as x approaches negative infinity of f of x, as my x's are getting more and more and more negative, as I'm going way far to the left, my graph seems to be leveling out at that horizontal asymptote. This is really all about horizontal asymptotes, this section. Horizontal asymptote at negative 2, so I'm going to say that that limit equals negative 2. I don't care at all about what's going on in the middle, just far to the right if I'm doing the limit as x approaches infinity, and far to the left as I'm doing the limit as x approaches negative infinity. Can you please quickly take a look at that handout that I hopefully remembered to give you, the one that says graphical and numerical limits at infinity, and see what you can do with 1 and 2. We haven't talked about the table, but I think you can kind of figure out what's going on with that table of values as well. See what you can do. So 1a, what did you say for the limit as x approaches infinity? Well, as x approaches infinity, I'm going far to the right. Looks like I'm getting close to a y value of 1. I'm going to make that 1. What did you say for the limit as x approaches negative infinity? Negative infinity, well, I'm going far to the left. I'm over here. Looks like it's kind of leveling out at a y value of 2. There is a lot of other stuff going on in this graph. There's a vertical asymptote there, another one there, kind of like some sort of sine behavior. I don't care about any of this stuff. Just what's happening far to the right for A and far to the left for B. 2a, what did you say for the limit as x approaches infinity? Well, as I'm going far to the right over here, looks like my y values are approaching 2. I'm going to say that equals 2. What is the limit as x approaches negative infinity? Looks to me like I'm approaching a y value of negative 2 over there. The table of values, this is a different table than how we usually look at these things. I'm trying to show you as x goes from 1 to 10 to 100 to 1,000 to 10,000, as the x's are getting bigger and bigger and bigger and bigger, you notice the y's seem to be leveling out. What did you say for the limit as x approaches infinity? Looks to me like those y's are leveling out at about 2. And the limit as x approaches negative infinity, looks like those are getting close to negative 2. Okay, so limits at infinity will give us some language to talk about horizontal asymptotes, those values I get really close to, far to the left and far to the right. What we're going to spend most of the rest of today looking at, though, are some analytical limits. Back in your notes, there is one big idea that's going to take us through all of this. Our big idea to analytically evaluate limits at infinity or negative infinity. One big idea that's going to take us through all of this. The limit as x approaches infinity of 1 over x. Think for a moment. 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. The bigger the x value gets, what do you think this gets really, really close to? 1 over 1,000,000,000, 1 over 1,000,000,000,000, 1 over something bigger than that. We're getting smaller and smaller and smaller, and we're going to get close to 0. And if you don't believe this, go to your calculator. Do 1 over 1,000,000, 1 over 1,000,000,000. The bigger that bottom gets, the closer your answer gets to 0. Well, what about the limit as x approaches negative infinity of 1 over x? What's 1 over negative 1,000, negative 10,000, 1 over negative 100,000, 1 over negative 1,000,000? What's that getting closer and closer to? That one is also going to get close to 0. These are the two ideas we're going to need to take us through all of this stuff. First example I'd like to look at. Let's look at the limit as x approaches infinity of 4 minus 1 over x plus 2 over x squared. The limit as x approaches infinity of 4 minus 1 over x plus 2 over x squared. Well, by my properties of limits, I can really split this into 3 different limits, and I'm going to see what happens there. If you plug a huge number into the constant 4, you're just going to get 4. If you plug a huge number into 1 over x, 1 over a huge number, from what we saw over here, is 0. So we're going to get 4 minus 0. If you plug a huge number into the last part, well, the bottom is an even bigger number. 2 over a really, really, really big number, also going to give you 0. This limit is going to equal 4, which means far to the right on our graph, we're going to get close to a y value of 4. Let's look at one a little bit harder. The limit as x approaches infinity of 2x minus 1 over x plus 1. Get that copied down. The limit as x approaches infinity of 2x minus 1 over x plus 1. Okay, by the way, and I think I should have mentioned this before, we are not allowed to plug in infinity like a number. You cannot write things like 2 times infinity minus 1 over infinity plus 1. That's not good notation, and I'm going to add something on to the limit notation rubrics that make a comment about never plugging in infinity like a number. But what we should see is if I was to plug in a huge number, the top of this thing, 2 times a huge number minus 1, that's a huge number. The bottom of this thing, a huge number plus 1, also a huge number. What we get is what we can call the indeterminate form, infinity over infinity. Again, the name for this is an indeterminate form. This is just like that indeterminate form we saw of 0 over 0. Indeterminate means if we get that, well, we haven't really determined what our answer is. Our answer to this problem could be 0, or it could be infinity, or it could be 52, or there are many different options for this thing. This tells us not so much in and of itself. We need to do a little bit of work to make sense out of this. I'm going to show you the formal way of dealing with this, but then we're going to look at a shortcut for dealing with these things. What I'm going to do here is I'm going to divide the top and bottom of my limit by x. This is going to give me the limit as x approaches infinity of 2x minus 1. I'm going to go and divide that thing by x over x minus 1, and I'm going to divide that thing by x. Well, if you do that, that gives us the limit as x approaches infinity. Well, 2x divided by x, that's just 2. Negative 1 divided by x is negative 1 over x. If we do the same thing in the denominator, actually you go do that. What do you get in the denominator when you divide x plus 1 by x? Should give you 1 plus 1 over x. Well, now if I try to plug in a huge number, I'm not going to get that infinity over infinity indeterminate form. On the top, if you plug in a huge number, well, what is 2 minus 1 over a huge number? That should give you 2 minus 0. I'll clean that up in a moment. What do you get when you plug a huge number into the bottom? That should give you 1 plus 0. This limit is just 2 over 1. This limit is 2. To find these limits at infinity, the formal way of dealing with things is by doing some division. I'm going to divide the top and bottom by the variable that has the highest power in the denominator. There's a much easier way, though, to deal with this. And we're going to look at this shortcut now. We're going to call this our shortcut. Am I still on the screen? Yes, I am. Shortcut for limits at infinity of rational functions. What you should notice in the last problem we looked at, that minus 1 and that plus 1 didn't end up doing anything to my limit. All that really mattered were the leading terms on the top and on the bottom. My shortcut for dealing with this in general is if I want to do the limit at infinity of a rational function, I can just look at the limit of the ratio of the leading terms. I'm going to look at the limit of the ratio of the leading terms. For example, the limit as x approaches infinity of 5x cubed plus 1 over 10x cubed minus 3x squared plus 7. The limit as x approaches infinity of 5x cubed plus 1 over 10x cubed minus 3x squared plus 7. What I could do is divide everything by x cubed, but I want to use this shortcut way. which is really how we're going to deal with these things moving forward. This is going to equal the limit as x approaches infinity. I'm going to ignore everything on the top and bottom other than the leading terms. This is the limit as x approaches infinity of 5x cubed over 10x cubed. Because if we did do the division, everything else would end up just being a zero thing once I took my limit. Well, we can simplify this. We can make this the limit as x approaches infinity of 5 over 10 x cubed over x cubed. Well, the x cubes cancel. The 5 over 10 just becomes 1/2. Well, now we can take our limits. Plug a huge number into the constant of 1/2. Well, if you plug anything into a constant, you just get your constant, and my limit is going to equal 1/2. This is the work I'm going to need to see, and of course I'm being good about my limit symbols until I actually go and think about plugging in a huge number, which is where I'm getting my 1/2 from. Let me show you 2 more of these, and then the rest of this video will be some shortcuts and talking about horizontal asymptotes. Next one. Let's do the limit as x approaches negative infinity of 2x to the 10th minus 1 over 10x to the 11th minus 3. The limit as x approaches negative infinity of 2x to the 10th minus 1 over 10x to the 11th minus 3. Well, I'm going to look at the limit of the ratio of the leading terms. This is the limit as x approaches negative infinity of 2x to the 10th over 10x to the 11th. You see if you can go from there. What do you have for the limit as x approaches negative infinity? Well, this is going to simplify to the limit as x approaches negative infinity of 2 over 10 is just 1/5. And x to the 10th over x to the 11th is just an x in the bottom, so I'm going to get this problem. And if I plug in a negative huge number, the bottom becomes a negative huge number, and 1 over any sort of huge number, positive or negative, just gives me 0. Your limit is going to equal 0. Again, make sure you're not showing things like 1 over 5 times infinity. That is not valid notation. I will take off points if I see that anywhere on your paper. One more like these before we start some variations. Limit as x approaches negative infinity of negative 3x to the 12th plus 2x over x to the 11th minus 2x to the 4th. You see what you can do here. After looking at the limit of the ratio of the leading terms and simplifying, we're getting negative 3x. Negative 3 times a negative huge number. Well, a negative times a negative is a positive. You plug in a huge number, you're going to get a huge number. Your answer should be positive infinity. Sometimes we'll get 0, sometimes we'll get some sort of infinity, sometimes we'll get a non-zero or non-infinite idea for an answer. Let me show you some variations. And I have 3 different types of variations we're going to look at. Our first type will involve some square roots. And the first thing that I have to do is fix something that you learned in Algebra 1, Algebra 2, that wasn't 100% correct. The idea here is the square root of x squared. Well, I actually don't just want to say that it equals x. There were some like conditions on that made it equal x in Algebra 1. The square root of x squared is actually the absolute value of x. Let me give you some examples. If I have like the square root of 2 squared, well, that's the square root of 4. That's going to give me 2. If I want to do the square root of negative 2 squared, that's the square root of 4. That's also 2. We can't just say the square and the square root cancel each other out. That's true if the thing inside is something positive. But if the thing is negative, we need to take the absolute value of that x value. With this in mind, let's take a look at the limit as x approaches infinity of 3x minus 2 over the square root of 4x squared plus 1. I'm going to do the same thing I have been doing, and I'm going to look at the limit of the ratio of the leading terms. I'm going to say the limit as x approaches infinity of 3x over the square root of 4x squared. That's going to be my first step. This is going to equal the limit as x approaches infinity of 3x over, well, square root of 4 is just 2, and the square root of x squared is the absolute value of x. So I'm going to write that. As we saw with other things, I can't just make an x and an absolute value of x cancel. I need to rewrite this without absolute value bars, which really means I need to decide, is this thing x or is this thing inside the bars negative x? No, sorry. If when I take the absolute value, if I just want to remove the bars or if I want to change the sign of the thing that was inside there. Well, what I'm going to look at is I'm doing the limit as x approaches infinity. The absolute value of some positive huge number is that positive huge number. You just leave things alone. Because of that, I can make this the limit as x approaches infinity of 3x over 2x. Well, finish it off. We'll cancel the x's, and we're going to get 3/2 for our answer there. Let me show you 2 more square root problems. The limit as x approaches negative infinity of 3x minus 2 over the square root of 4x squared plus 1. So really the same problem. I'm just doing the limit as x approaches negative infinity. I'm going to start this the exact same way. This is the limit as x approaches negative infinity of 3x over the square root of 4x squared. This equals the limit as x approaches negative infinity of 3x over 2 times the absolute value of x. If you go to take your limit, is the thing inside your bars a positive or is it a negative? Well, I'm plugging in a negative huge number. That thing inside the bars is negative. How do you take the absolute value of a negative number? You change its sign. So this is going to equal the limit as x approaches negative infinity of 3x over 2 times negative x. So I really could just say negative 2x. Remember, this isn't really like a negative. This is a change the sign of something that is already negative symbol. Finish that off. What's your limit? Limit here should end up being negative 3/2. You're going to try one on your own. See what you can do here. everything inside the bars is negative, which means I have to change its sign. This is the limit as x approaches negative infinity of negative 3x over negative x. The x's cancel. Your answer is going to be positive 3. That was our first variation. Next variation, trig. First example, the limit as x approaches infinity of the sine of x. What is the sine of a huge number? Yet you actually can't do this problem. Sine, remember, just kind of keeps bouncing between -1 and +1 and taking on all the values in between. So the sine of a really big number might be 1 and go a little bit further, and then it might become 0, and then it might become -1, and this limit does not exist. I probably shouldn't say equals. That limit does not exist. However, let's look at this one. Let's do the limit as x approaches infinity of the sine of x over x. Limit as x approaches infinity of the sine of x over x. So the top doesn't really exist because we're bouncing between -1 and +1 and everything in between. The bottom is a huge number. Well, the lowest possible answer that I could get for a sine problem is -1. What's the highest possible answer you could get from a sine problem? I think that's going to be +1. And again, sine just keeps kind of varying in between those, but I know the lowest the top could be is -1, and the highest it could be is +1. Well, look at this thing I can do. This is going to go back to something we did a couple days ago. I can say that the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of the sine of x over x is less than or equal to the limit as x approaches infinity of 1 over x. I know that since the sign is between -1 and +1, I can set up an inequality that looks like these. And I'm trying to find the thing in the middle. What is the limit as x approaches infinity of -1 over x? Should be 0. What's the limit as x approaches infinity of 1 over x? Should also be 0. Therefore, what is the limit in the middle going to have to be? That should be 0. You remember the name of the theorem that guarantees this? I hope you just said, by the squeeze theorem. The squeeze theorem. Why don't I say by the squeeze theorem? Okay, we have one more variation to look at, and then we need to look at some stuff with horizontal asymptotes. Our third variation we have to be able to deal with are exponential functions. And I'm going to show you 4 of these. The limit as x approaches infinity of 2 to the x plus 1 over 4 plus 5 to the x. And our rule before about the limit of the ratio of the leading terms only works if we have a rational function where the top and bottom are polynomials. That's not what I have over here, so that's not going to work. You should notice that if you plug in a huge number, the top is huge, the bottom is huge, so this is that infinity over infinity indeterminate form. Here's what we're going to notice. If I plug in a huge number where the x is 2 to a huge number, that's a huge number. The plus 1, doesn't really change it by much. The 2 to the x is so much bigger than the plus 1. Similarly, on the bottom, the 5 to the x is so much bigger than the 4. So I'm going to ignore the 1 and the 4. And I'm going to get the limit as x approaches infinity of 2 to the x over 5 to the x. Plug in a huge number, top is huge, bottom is huge. It's still that infinity over infinity case. But by my laws of exponents, I can say, rather than 2 to the x over 5 to the x, I can say this is the limit as x approaches infinity of just 2/5 to the x. Take a moment, go to your calculator, and figure out what 2/5 to the 100 is, to the 1,000 is, to the 10,000 is. What is this limit getting really close to? You should see it getting really close to 0. Let's do the limit as we approach negative infinity. As we approach negative infinity of 2 to the x plus 1 over 4 plus 5 to the x. What is 2 to a negative huge number? Well, let me do some work on the side. 2 to like the negative 1,000 is 1 over 2 to the 1,000. And as this gets more and more negative, 1 over 2 to a million, 1 over 2 to a billion, 2 to the x, if x is approaching negative infinity, should get really close to 0. I'm just going to say this is 0 plus. What happens if I plug a negative huge number into 1? You just get 1. On the bottom, I have 4 plus. What is 5 to a negative huge number? That is also 0. I'm going to get 1 over 4. I'm going to get 1/4. This problem worked very differently on the right side versus on the left side. 2 more of these. The limits as x approaches infinity of 4 to the x minus 3 over 3 to the x plus 2. Because I'm approaching positive infinity, 4 to a huge number is so much bigger than minus 3, and 3 to a huge number is so much bigger than 2, I can ignore the constants, and I can just make this the limit as x approaches infinity of 4 to the x over 3 to the x. See if you can proceed the way we did in that first example. We'll make this the limit as x approaches infinity of 4/3 to the x. 4/3 to a huge number? Well, this is different than that first example. If you have a fraction that is between like 0 and 1 that you raise to a huge number, you're going to get closer to 0. But if I have a fraction greater than 1 that I'm raising to a huge number, 4/3 times 4/3, well, that makes it bigger. Times another 4/3 makes it bigger still. This one is going to give you infinity. And if you don't believe this, go to your calculator. Do 4/3 to 100, to 1,000, to the 10,000. That's going to be infinity. Let's look at the limit as x approaches negative infinity of 4 to the x minus 3, same problem, over 3 to the x plus 2. This one is more like our second example. 4 to a negative huge number is 0. See if you can proceed from there and submit your answer. You should be getting negative 3/2. I'm going to need to stop the video because I can't record for more than like 40-ish minutes, and then there's one other very short video you're going to watch on finding horizontal asymptotes.